So I'm going to talk about attack cost models, which is sort of a topic that's come up repeatedly throughout the NIST PQC competition. So the basic idea. So we'll talk about why is this relevant? We're going to talk a little bit about how things used to be simpler. And then we're going to talk about the PQC standardization process and some issues regarding things like Grover's algorithm that make it so that you have to think a little bit harder about how many bits of security or whatever you have in your system. So we'll talk about a bit of the motivation that led to kind of what we say in the call for proposals, the 5 security strength categories. And then we'll talk about, in particular, memory intensive attacks that come up that have been sort of the most tricky to deal with. And we'll talk about some of the algorithms where that's come up. And if we have more time, we can get all speculative and talk about physical limits of computation and how you might think about trying to measure the cost of memory with current technology. So the basic idea is when you measure attack costs, the idea is, the first point is you want to make sure that your crypto system is hard to break. So all cryptography, at least where you have a reasonable sized key, is based on some kind of computational assumption, and so you have to figure out how much computation your adversary can afford and make sure they have to do more than what it takes to break the thing. But generally, you want to go beyond that because you generally don't actually know what the best attack is. You know what the best attack anyone's found so far is, but people come up with better stuff all the time. And in line with that, you actually kind of want to measure precisely what the current attack cost is so that cryptanalysts can publish a paper and say, this new attack shaves 3 bits of security off or something, something very small, so when you're improving. And above and beyond that, you having clear information on how much it costs to attack a crypto system helps with both designing crypto systems, so you can specifically say, I want this much security, and when you find out that you don't have enough security, when do you pull the standard? And so measuring that is important for that kind of thing. So in the old days, things were kind of simple. You just said, assume your crypto system is a block cipher. How big a key do you have? So if you assume the best attack is key search, then if you have a 56-bit key, it costs 2 to the 56 operations to break it. So okay, you have 56 bits of security. That's really not enough. Okay, but there were standards like that. Then there were standards designed for 80 bits of security. Those can currently be broken for something like $1 million. And then you get into 128 bits of security, which really, if it actually has 128 bits of security, it shouldn't be breakable. And then there's sort of security levels beyond that, which really, it's very hard to imagine technology that's designed to break 256 bits of security. So that's for security margin in case there's cryptanalysis. So that brings us to the present topic, which is the NIST Postquantum Cryptography standardization process. So that started around 2016 when NIST started paying attention to the fact that if you have a quantum computer, you can use Shor's algorithm to break basically all the public key crypto that's deployed, and certainly all that has been standardized other than hash-based signatures at this point. So NIST wanted replacements for these. And we had previously run competitions to design block cipher and a hash function. So the idea is you issue a public call for proposals, people send in candidates, and you evaluate them for a long time and pick something to standardize. Now, the PQC standardization process focuses on public key. What about symmetric crypto? Well, so there are quantum algorithms that improve the best attacks on symmetric crypto. So Grover's algorithm breaks AES 128 in 2 to the 64 operations. And there's a slightly more advanced application, basically, of Grover's algorithm called the BHT algorithm that finds collisions in a 256-bit hash function in 2 to the 85 operations. And so if you remember from the last slide, 64 bits and 85 bits of security really are usually not enough. But these algorithms actually probably are okay. And the reason is because Grover's algorithm is actually more expensive than the top line number might suggest. So, so with a brute force key search, you can parallelize that as much as you want. If you have to do 2 to the 80, look for 2 to the 80 keys, you can have a trillion machines and each one only has to check a trillion keys. But with Grover's algorithm, the idea is you're going to do some kind of an iteration, and it's kind of an inherently serial thing. You initialize a quantum register, you do something which costs about the same as running AES on a quantum computer, and after you do it about 2 to the 64 times, then you can measure the register and you have a high probability of getting the key. But if you only go, a small fraction of the way, then your probability is actually much lower. Your probability is actually increasing quadratically with the number of iterations you do. So if you do, 1,000th of the operations you need to do, then your probability of success is like 1 in a million. So you generally want to run it all the way. And by the way, you can't just measure halfway and hope for the best, and then if it doesn't work out, just keep going. You basically destroy all progress when you measure. So yeah, so this is a situation where in order to get the best complexity, you would need to do 2 to the 64 operations in series, which is actually hard. If you tried to run it on a classical computer with no kind of parallelism, that would actually take several years. And it's even worse because you have to run it on a quantum computer, and quantum computers, you have to supercool them, so they're probably a little slower, and then you have this error correction on top of it. So maybe you can do like 2 to the 40 things in series. And this means that you're going to need to parallelize. And if you parallelize, so one way you can do it is you divide the key space up. and then each processor can search 2 to the 80 keys. Well, that means you need 2 to the 48 processors. The other option is you just stop after 2 to the 40 iterations, in which case your success probability is 2 to the minus 48. And so either way, you're not doing 2 to the 64 AES operations. If you have a depth limit of 2 to the 40, you're doing 2 to the 88. And the trade-off there, both of those options are basically optimal, as was shown by Zalka in 1997. And then there's also hash collision search, and the best known classical algorithm. So the best classical algorithm for collision search parallelizes just fine. But for a 256-bit hash, it takes 2 to the 128 operations. Now there's the BHT algorithm, which uses a quantum computer, and it does 2 to the 85 SHA operations. But just like Grover, this all has to be done in series if you want to get that complexity. And also, each one of these operations comes with a random access query to a memory that's 2 to the 85 hash function states, or 2 to the 90 bytes. And so that's going to have some extra latency, because a very large memory like that, those bits aren't all in the same place. So you gotta, if you're reading a bit of that memory, you have to, it has to get from point A to point B, and that takes time because the speed of light is finite. So that's going to induce actually a lot more latency. Now, analyzing all this stuff gets a little bit complicated, but the likely conclusion is that really with any conceivable quantum technology, the classical algorithm is going to be, either just straight up the best algorithm or very close. So in response to this situation, NIST defined 5 security strength categories. And the idea was, we would like to come up with some kind of way of measuring security which correctly assesses that SHA-256 is almost certainly okay, and AES-128 is probably okay. But we don't want to just allow things to have 64 or even 85 bits of security, because if that's a classical attack and it parallelizes, that's definitely not enough. So the idea was simply, we said, well, we're not exactly sure how to measure security. There's different ways, but however you're doing it, we want to make sure for things that are category 1, they're as hard to break as AES-128 when you're just looking for a key, for the key based on a small number of plaintext ciphertext pairs. Should be, for category 2, we said at least as hard as finding a collision in SHA-256, however you do that, and so on. And the idea there is, for any plausible way of measuring attack costs, you want to make sure you are above the threshold. And so if you can come up with a plausible way where it's not as strong as AES-128, then it's not category 1. But then that brings up the question, okay, well, what's plausible? So, the way we define the categories sort of explicitly mentioned that parallelism might be an issue. But another thing that could be an issue is attacks that require a lot of random access to memory. Now, in the case of the attacks that we use to define the categories, you really don't need a lot of random access to memory. I mean, if you parallelize it, you will use a lot of memory, but it's going to be all accessed locally, so it doesn't really add much to the cost. However, the best classical attacks on a lot of the post-quantum candidates, and for that matter, a lot of the quantum attacks, do need a lot of random access to large memory. And so there's some ways of measuring costs that say that this is quite expensive. And realistically, it probably is. So then the question is, if something that is discounting the cost of memory access says that an algorithm is not quite meeting its security level, then you don't know whether, you know, it really might meet its security level if you're measuring things realistically. So if you can argue that the things that say it's not meeting the security level are not potentially relevant to practical security, as the call for proposal said, then you can get more efficient parameters for a given algorithm. So things that have come up, so ways of measuring attack costs that have come up include the RAM model. There's circuit models that can be local or non-local, and there's also models that assume geometric constraints. For example, two-dimensional models like time times area, and three-dimensional like time times volume. So the RAM model is certainly the most common way of measuring the cost of an attack, and it's fairly intuitive to anyone who's programmed in assembly, because the idea is if you have instructions for doing various arithmetic things, and then you also have an instruction for reading and writing from memory. So if you just sort of think of each thing as an instruction, then that's basically what the RAM model is. So the idea being that reading and writing from memory just cost the same as any other operation. However, in real systems, as the memories get very large, so even when you're talking about DRAM on a single processor, the access times are significantly more than what you'd expect for just a basic assembly instruction. And when you get into really big things like supercomputers or data centers or something like that, then you have things that are, just not in the same place, pretty far apart. And so you have large access times, you're consuming more energy when you read or write from memory, etc. Now, there's also circuit models. And it's interesting, circuit models actually impose a very large cost on memory access, especially if you can't parallelize it. So hello? Is there a question? Okay. So here the idea is you have your bits and they're just sort of sitting there, and you can pick out any one or two bits and do something to them. And this is actually the most common way to measure quantum attacks. However, if you look at memory access, well, if you say, give me a 50-bit address, I want something in a 2 to the 50 size memory, well then, if you don't know exactly what the address might be, then you need to touch every single one of those 2 to the 50 memory locations. So the cost is actually proportional to the size of the memory. Now, if you can parallelize the thing so that you have 2 to the 50 different processes accessing that memory in parallel, then each memory access is pretty small, because you can think of the whole thing as a network that's handling whatever it needs. This was actually shown explicitly by Beals et al. That you can, if you can parallelize it, then the cost of memory is not so much, but you need to parallelize it. Okay, so that's. But yeah, even this is not necessarily so realistic. So there's also two-dimensional models. So we have so one thing to keep in mind is, so the gate, so both of the models we talked about previously don't pay attention to how far apart bits are. The assumption is a bit can be moved from point A to point B for effectively zero cost. So for a 2D model, you basically have the same kind of thing, but you assume everything's arranged two-dimensionally. And why do we say 2 dimensions instead of 3? Well, so the idea is each time you do something, it consumes energy and dissipates heat, and that heat has to go somewhere, and it moves at a finite speed. So if you try to put things in 3 dimensions, then the heat is sort of interfering with your thing as it's trying to get out, and whereas in 2 dimensions you can just immediately get it off through the surface. That said, depending on what you're doing in your real process, it's quite possible that the heat dissipation isn't a problem, and you can actually use the 3rd dimension. Then there's also 3-dimensional models for that reason. But you just have to keep in mind that in a lot of cases, if you're doing something memory intensive, then you probably can't actually arrange things. Yes, something that consumes energy. So if you probably can't have active processors in 3 dimensions everywhere, at least if you don't slow them down. Now, there's a particularly influential 2D model, which is actually a little different from a time times area or a circuit model with an imposed geometry that was proposed by the N-True prime team, and this is explicitly based on energy consumption. And so the idea here is moving bits around on, at least in wires that are on a chip, has a certain cost, and density memory density is limited, at least if you're using DRAM. And so based on some published figures by David Dunning from Intel, the N-True prime team estimated that if you do random access to a memory of size m, it should cost the same as square root m bit operations times 2 to the minus 5th. This was subsequently taken up by the Rainbow team, which was in response to an attack on Rainbow. And this cost was used to argue that the Rainbow parameters were still secure. And this does actually seem like a pretty plausible way of measuring the cost of memory for reasonably small systems. However, some attacks involve truly colossal amounts of memory, like 2 to the 90 or something. And at that point, it doesn't really make sense to be doing moving your bits on wires. You should probably be using fiber optics at that scale. And that has a lot less cost per unit length. And likewise, the memory can also get denser. You can use something like flash or solid state drive. You wouldn't use that for a small system because the access cost, like right at the end, is pretty large. But if most of the cost is moving the bit, then you just want it denser. And solid state drive or even hard disk is probably going to be better. So, so that brings us to some case studies. So the first thing we'll look at is Psych. And so Psych is it's a NIST PQC candidate based on the supersingular isogeny Diffie-Hellman problem. And the parameters are set by the claw finding variant of the Van Oorschot Wiener algorithm. And this is a pretty old algorithm. Even as applied to SIDH, it was known pretty much from the beginning of investigation of that. It parallelizes quite well, and the memory access is local. So, in fact, it doesn't really matter if you're using RAM model, time area, time volume. Everything should come out the same. So why is something interesting happening here? Well, the interesting thing is that the attack runs better when you have more memory, and the submission in estimating the cost of the attack says whatever's going on, the memory is never going to be more than 2 to the 100 bits. So a member of the Psych team and along with some other people went further and published a paper at Crypto where they set the security based on the assumption the attacker only has $1 billion worth of hardware, resulting in estimates that the amount of time it would take to break things would be billions and millions of years. So the memory limitation is actually does have a pretty strong effect on how aggressive you can be with your parameters. So, but then the question is, how reasonable is it to assume 2 to the 100 bits of memory is the largest the memory is going to be? And so I think we basically concluded, yeah, it was probably okay if you're talking about category 1, but if you're talking about category 3 or 5, then there's strong physical reasons to think that if you want this attack to actually finish in a reasonable period of time, like a few years, then there's no way the attack depth is going to be more than something like 2 to the 80. And the requirement for the number of bit operations you're going to need to do at category 3 is 2 to the 207. And that means that you're automatically going to have 2 to the 127 bits just sitting there at some point. You know, there's sort of no way of avoiding having the number of gates, you know, being less than width times depth for any kind of a circuit implementation. Category 5, same thing, but worse. You need at least 2 to the 192 bits of memory if you think the attack's going to finish in 2 to the 80. Now 2 to the 192, category 5, just everything gets ridiculous. So it's probably better to relax the 2 to the 80 slightly than to say 2 to the 192 bits of memory is reasonable, because if you count the atoms that are outside the sun and the solar system, you only get to about 2 to the 180. So even if you assume 1 atom per bit of memory, you still can't do it except by trying to compute inside the sun or something, and it seems a little crazy. So my personal opinion is that if you're going to have memory limits at category 3 and 5, something more like 2 to the 140 or 2 to the 180 for category 5 would be reasonable. And if you do that, then the category 3 parameters are below their security target by 20 bits of security, and the category 5 parameters are below by 40 bits of security. And we sort of noted this in the round 2 report, but Psych didn't revise their security estimates. So if we standardize that, that issue might, will need to be resolved. And so I don't know, NIST might claim that if it standardizes, NIST might claim that these are not, category 2 and 4 or something. So another thing that came up, so we mentioned Rainbow before. They were broken early in the 3rd round by Bulens, at least in the RAM model. The security dropped by 20 bits at category 1, 55 bits at category 5. And the attack was about as memory intensive, relative to computation as the previous attacks. So if you measured it in some other way, it's probably losing 20 to 55 bits of security similarly. But the Rainbow team said, well, we set our parameters based on the RAM model. However, that's not necessarily realistic. It costs something to access the memory, and they did an estimate and said if you take into account memory costs, then they said, okay, we're still meeting the security. Now, a paper that actually I was on tried to analyze this further, noting that every time you access memory, you don't necessarily have to access the full memory. You can divide the memory up so that most of the operations can be done by processors that are closer to the memory than one central processor would be. And based on some pretty extensive analysis there, looks like even if you assume the N-true prime's estimate for what it costs to access a memory, then you're probably still below the security targets. All this ended up being not super relevant because Bulens at the end of the 3rd round came up with a much better attack, which you can see from the title, Breaking Rainbow Takes a Weekend on a Laptop. You didn't have to get quite as speculative about what does memory really cost. So, but since we're talking about cost models, we can look at sort of what the issues were involved in whether, based on the Bulens 2020 attack, Rainbow was meeting its security targets. And so the most expensive, so the cost of the Bulens 2020 attack is basically you're doing many times a matrix vector multiplication between a high dimension, by a very large matrix and vector. Now the matrix is very sparse, and the coefficients can be cheaply generated on the fly. So you don't actually have to store the matrix. So the size of the memory is determined by the vector. And so that's what the Rainbow team did. They assumed the memory size is the vector dimension, and they assumed for every non-zero matrix entry, when you're going to have to multiply that by a vector element, and every time you do that, you're going to have to access, do a random access query to a memory the size of the vector. However, the follow-up paper, the BBCPS TV 2021, you determined that you could organize the memory in such a way that it's broken into several thousand smaller pieces, and the matrix row that has non-zero entries, most of those non-zero entries, or actually all of those non-zero entries, are only going to be in 10 or 20 of the several thousand partitions. Then you could have a processor in charge of each memory partition, and it could add up all the coefficients, partial sum for each of the 10 or 20 partitions. And so you only need to send 10 or 20 things long distance instead of a few thousand. There were some other optimizations, like the fact that the memory access patterns were exactly identical for groups of rows of about 50 to 100. And so you only had to move those memory locations once, and you could keep them in kind of small caches. So that saved a lot. And also, you didn't have to, you could, when moving things long distances, you could block them into large messages that could travel together. And so sending addresses around, which was a big part of the Rainbow team's original cost estimate, could be made negligible. So we can now look at how did things work out. So started out at the start of round 3, we had 147, 217, 281. Is the log of the number of bit operations. So Buelen's 2020 is, you can see it again, the RAM metric is dropping things quite a lot. But you can see based on the Rainbow team's estimates, the actual security is, between 25 and 50 bits of security higher. But if you actually investigate optimizations, you get 10 or 20 of those bits back. But a new attack is really quite powerful. So Buelen's didn't analyze it in any kind of complicated memory metric, but even so, you can see you're losing something like 60 bits of security at the lowest security level, and that's memory is just not going to make up for that. Okay, so what is potentially more relevant is lattices. And so parameters of lattice are based on lattice reduction algorithms, and those are following a basic framework, the BKZ algorithm, and you use either sieving or enumeration within that. So enumeration is an algorithm that where you don't really need a lot of memory. Memory is not adding much to the cost. You just need it when you want to parallelize the thing. But the complexity has this extra log factor in the exponent, whereas sieving doesn't have that, but it's very memory intensive. So the basic idea of sieving is you come up with a big list of lattice vectors, and if you have a pair of lattice vectors that are close enough, you can take the difference between those two lattice vectors, and it's shorter, and you can replace it on the list. So the first, one of the earlier sieving algorithms, the Wien-Wittig sieve, had a complexity with a 0.415 as the constant in the exponent. And it just compared everything to everything to try to find two vectors that were close together. And that one's been shown to use local memory access. But then there are a series of more complicated sieving algorithms, and the idea there is you don't just compare everything to everything, you kind of separate your list of vectors into buckets and only compare the things in the buckets, in the same bucket. And the more selective you are, kind of the more efficient it is. And so this got the constant all the way down with the BGDL algorithm to 0.292. However, something a little less advanced in a presentation by Ducasse was conjectured, at least, to only need local memory access. So Lattice Security had been measured by Core SVP, and Core SVP was supposed to kind of take into account the fact that a lot of things seemed like they had room for optimization. So in reality, you might have to do the sieving oracle a lot of times, but there were a lot of ideas for making it fewer, for example. So the idea there was just say, okay, assume you have to do sieving once. Okay, there's a 0.292 in the exponent. Don't worry about any constant factors in the cost, and you get a some rough estimate of the bits of security. So it was argued that there was more bits of security, although that got complicated because the number of dimensions you actually need is not the BKZ block size, but something a little smaller to the dimensions for free trick. So yeah, so things, but I think it's still probably the case that the core SVP number is a little bit below the actual bits of security. But this was, not knowing the constants, was kind of a weird situation because you'd sort of have a rough estimate of how many bits of security, but not know whether you were high or low. So there were some, pretty explicit efforts to do this in the RAM model. So in particular, the Kyber spec had a pretty detailed way of trying to measure this. But they also said, well, there's certain optimizations that we don't know what's optimal, and they might make certain things more complicated, and there's certain costs that aren't accounted for. And so these could account for, up to plus or minus 15 bits in their security estimates. But they also mentioned, without an estimate of how many bits it's going to affect, going beyond the gate count metric, and that means explicitly taking memory into account. And so there were various ways this was handled. For example, N-true prime in round one, and ntrue also in round one before it merged, basically ignored sieving based on the fact that the current implementations of enumeration were better in practice. This didn't really age well, so the currently, even for practical parameters, sieving is better. Then another thing, so the ntrue submission had kind of two ways of measuring. One was just basically similar to core SVP, but the other one was saying if you didn't know how to make the memory access completely local, then you would just ignore the attack. And that seems kind of dangerous because clearly less work had been put into trying to optimize for local memory access. And it also seemed like you should be able to get time times area down to something smaller than, so there was, whether you counted Ducaus's conjecture or not, change the constant from 0.35 to 0.415. Ntrue prime later on assumed 0.396, just based on the assumption that if you have square root latency for a memory access, then you should be able to take anything that has 0.207 on the memory and 0.292 on the time, and have 0.396 on the time counting memory. So in summary, for lattices, there's actually been a lot of work on lattice cryptanalysis, which is great. The exponential part, so the constant in the exponent, has been stable since 2016. And it's likely that if you count memory, the parameters, are not even are pretty far above their targets. Makes the attack cost significantly more. But the bad news is even the RAM model has a lot of uncertainty, and there's been a lot of improvement in the sub-exponential part of the RAM complexity, dimensions for free, progressive sieving. There's recently some improvements in the dual attack. And moreover, while memory probably does increase the complexity, how much hasn't really been investigated with the same the same amount of work. So there's a lot more uncertainty about how memory is going to affect things. So let's see. So I think we're getting kind of late in time, so I guess I should skip the fun stuff, right?
Do you suggest 2 to the 140 bit as a memory limitation for category 3? Are we taking
yeah, I mean, my personal opinion is it should be something like 2 to the 140 or 2 to the 150 is about what I would, but that's not anything official to NIST. NIST has not made any such statement, but that's
And the question is, this estimation is taking into account one single machine or a distributed memory?
What, for the limit?
Yeah.
Oh, 2 to the 140 or 2 to the 150? Oh, that would be like the total amount of memory.
Okay, so distributed memory, I guess, right?
Yeah, I mean, and that's also orthogonal to any assumption about how much it costs to access that memory.
Okay.
Right. I mean, so it may be the case that if you have to do random access, the cost of the attack is prohibitive on that basis, even if the memory isn't that large.
Do you think one should take the potential for parallelization of an algorithm into account for the security estimate? And if so, how?
Yeah, I mean, so I mean, I think that that absolutely is relevant, which is right. I mean, that goes into why we think, for example, category 1 security, based on Grover's algorithm is still reasonable. It's based on the fact that Grover's algorithm doesn't parallelize well. I mean, the main danger of that is there's the question of, do we not know how to parallelize this just because we haven't tried very hard, or in the case of something like Zalka, have we actually proved there's some limit on how much an algorithm can be parallelized, or is it something in between, where there's been really a lot of effort, and so that's you really, yeah, in order to base your security on this algorithm doesn't parallelize, you want to be pretty sure it doesn't parallelize.
Okay. So there's another question. Basically, if the limitation of running quantum operation in series also apply for Shor's algorithm as well?
For Shor's algorithm, the main operation you have to do is a modular exponentiation. That's where most of the cost is coming from. And that does not, to my knowledge, parallelize well. In fact, there have been schemes proposed, so-called time lock puzzles, which explicitly assume you can't parallelize modular exponentiation. So I think it's fairly likely. I don't know if it's been proven. However, Shor's algorithm, the thing about Shor's algorithm is that the complexity is very, very low. It's you're doing on the quantum computer basically the equivalent of just running decryption the way the honest party would do. It's kind of the same complexity, other than the fact that you have to do it on a quantum computer. So it's very hard to come up with RSA parameters that, even taking into account things like parallelism, that you would have enough security.
So one last question is, you mentioned that psych parameters, psych P610 and psych P751 don't reach NIST security level 3 and level 5. If the question is, it will be the same for psych P545, 46, sorry, and psych P697, proposed by Longa et al.
Let's see. So, I mean, so those numbers, well, I don't know what those are claimed to me, but I mean, it should be, I mean, the size of the prime is basically the main security parameter for that. So it should be in between whatever it is. But yeah, I don't know the specific numbers for those.